Hi. So we're carrying on from where we were before the break, and at that time, we had finished talking about the inertia tensor for a rigid body, and we started barely, but we started talking about kinetic energy. Okay, so we'll continue talking about kinetic energy today. And the idea is we want to talk about the kinetic energy of a single rigid body in motion first. So here's our body, and it has its body frame. Like so. Okay, and so correspondingly, there's a vector r to the center of mass. Okay, and we're going to assume that the body is in motion. And so there's a curve in SO3 cross R3. Okay. All right, so we're interested in kinetic energy, which, and we're going to use to get started, the naive idea of thinking about what kinetic energy is, and that is just 1/2 mv squared, okay? And so the idea is going to be that we're going to think about first a point in the body, and sort of a little chunk of mass at that point, and we're going to label that point in two ways. First, we're going to have a vector in the body frame to that point in the body, okay, and we're going to call that chi. And then also, we're going to label that point with a vector in the spatial frame, and we're going to call that one x. All right. Okay, so if you want to think about how chi and x are related, well, first you have to account for the fact that chi is measured with respect to the body origin, and x is measured with respect to the spatial origin. So you have to translate by little r. And then you have to do a change of basis, because chi is represented in the body frame and x is represented in the spatial frame. And when you kind of work that out, this is what you get. Okay, so this relates the spatial coordinates of this point to the body coordinates of that point. Okay. All right, so now we want to write the kinetic energy. And so again, the idea is we're going to assume we have a little chunk of mass there, and that little chunk of mass we're going to represent by d mu of chi. Okay, and mu, so we have a body, which is, remember, given by a collection of points in R3, and then a mass distribution mu. And so intuitively, this gives you a little chunk of mass in the body location chi. So that's your m, basically. So now, well, a half is pretty easy to understand what that looks like. And then you need v squared. And so what's the v going to be? Well, it makes sense that you should measure kinetic energy in the spatial frame. Okay, and so v here is going to be the velocity of that point in the spatial frame, which of course is going to be x dot. Okay, and with x given like so, x dot is going to be Okay, like that. And so in this expression, chi here is a point in the body measured in the body frame, and so that's independent of t. Okay, and so the point is this is 1/2 v squared m, intuitively speaking. And so v squared is all of that stuff, and that's squared. Okay. So that's your kinetic energy, and we're going to think for the moment of kinetic energy of the body as being a function of time along the motion of the body. Okay, and so what we want to do is we just want to obtain a neater expression for that. All right. Oh, sorry, and so that's going to be the kinetic energy of the little particle at body location chi, and then to get the kinetic energy of the whole body, I integrate over the body. All right. Okay, so let's expand that and again obtain a nicer looking expression for it. Okay, so we're just going to do some calculation here. All right, so what we're going to do is we're going to expand the norm, okay, because it's norm squared, and so the norm squared is equal to the inner product. Okay, and if because we're using the fact that this is the Euclidean norm. Okay, and this will be then the Euclidean inner product. Okay. So let's go ahead and do that. All right, so we're going to integrate over the body. Okay, so so we're going to write this norm squared term here as the inner product of this with itself. Okay, and then we're going to expand the inner product, and so you're going to get the sort of inner product of this with itself, and you're going to get the inner product of this with itself, and then you're going to get a cross term. Okay, so the inner product of this with itself is just going to give you oops. Okay, and then similarly, the inner product of this with itself is just going to give you the norm squared of that. Okay, so and then you have the cross term. Okay, and that'll appear with a factor of 2 because you'll get the inner product of this with this, and then you'll get the inner product of this with this, and then by symmetry it's the same thing. Okay, so you get 2 inner product of r dot of t, r dot of t, chi, right, and then d mu chi. All right. All right, so now what we're going to do is we're going to look at the 3 terms in the integral here. And the first thing we'll do is we'll look at this one. Okay. Okay, so that term, so we want to look at the integral of r dot over the body of r dot of t, capital R dot chi mu. Okay, and so to expand this, we're going to use linearity of the integral first, and so we'll move the integral inside the inner product. Remember, the integral is with respect to chi, and this is independent of chi, as is this. So we'll move the integral inside the inner product, and then we'll also move it inside the matrix multiplication by r, because that's linear. Okay, so by linearity of the integral, this is r dot of t, r dot of t matrix r dot of t times the vector, which is the integral over the body chi d mu, like that. All right. Okay, so now we simplify this, keeping in mind that we are going to make some assumptions here. And there's two assumptions that we're making. We talked about this when we talked about the inertia tensor. So assumptions. First thing is we're going to work with use inertia tensor. About the center of mass. Okay, so you can take inertia tensors about any point, including points having nothing to do with the body. Okay, but it's going to be convenient here to use the inertia tensor about the center of mass. Okay, and then the other assumption we're going to make now is we're going to put the body frame, the origin of the body frame, so the body origin, at the center of mass. Okay, and so up until now, in this picture, the body frame could be anywhere. We could put the body frame out here if we wanted to, as long as the body moved with that frame. It doesn't really matter where you put the body frame. Okay, but now it matters. So for the purposes of doing these calculations, it's going to be convenient to make sure that the origin of the body frame is at the center of mass. Okay, so that point's going to be the center of mass. Okay, and then we're going to be taking the inertia tensor about the center of mass. Okay. So in that case, what this means is that the inertia tensor is the inertia tensor about the center of mass, which we write as IC, and IC applied to a vector u by definition is going to be the integral over the body. Okay, and so I'm going to use chi here because that's the variable that I'm using for the coordinates in the body frame, cross u cross chi. That's the definition of. Sorry, let me sort of write this out in full, just to emphasize what we're doing. So we have chi minus chi c. Okay, so chi c is the center of mass. Okay, cross u cross chi minus chi c d mu of chi. All right, so that's the definition of the inertia tensor about the center of mass. All right, so the point is that this point here is the body location in body coordinates of the center of mass. But assumption 2 is that that's 0. Okay, so with our assumptions, this is all right. So that's one thing that's true. It's also true that the center of mass, okay, so what's the center of mass? The center of mass by definition, and so let me use it as chi. Okay, so two things are true. First is that with these assumptions that I'm making up here, the center of mass chi c is equal to 0, and that's my assumption about where I've placed the body frame. But the center of mass is also equal to, by definition of the center of mass, okay, and this is equal to 0 with the assumptions that I'm making. So the upshot of that is that's 0. Okay. All right, and so So that's the cross term. Is 0 with the assumptions. Okay, good. All right, so that gets rid of that term. All right, so then we just have these terms that we're going to calculate. Okay, so we'll do the first one first, and that's relatively easy because remember, we're integrating here with respect to chi, and chi just doesn't appear there. So 1/2 integral over the body of norm r dot of t squared d mu of chi is, so, again, with respect to the integral, that's just a constant. Okay, and so this is just the integral of the function 1, and by definition, that's the mass. Okay, so that term has a simple meaning. It's with these assumptions that I'm making, this is just the translational kinetic energy of the body. Okay. So now we need to think about that term. Okay, so we'll do some calculation there. Okay, so 1/2 integral over the body of r dot t chi squared d mu of chi. Okay, so whenever we see capital R dot, we immediately want to get rid of it. The reason being that we prefer to use the other representations of angular velocity, which are body or spatial. Okay, so we're going to replace R dot with the body or spatial angular velocity, a capital omega or little omega. And you can sort of fiddle with this. You can do either. You'll end up with something that's correct. But as we'll see, it's convenient to use the body angular velocity. And kind of the reason for that is that we're integrating with respect to the body frame here. All right, and so we're going to use omega, the body angular velocity, and that's omega hat, which is R transpose R dot. Okay, and so that means that R dot is R omega, right? So that's the first substitution that we're going to make. Okay, so it's R of t, omega hat t, chi squared mu of chi. Okay. All right. Now, let's think about what this is. Okay, so this is R, okay, which is in SO3, so it's an orthogonal matrix, times this vector. Okay, let's just sort of lump this all as a single vector. Okay, so then what is, if you take a vector in R3 or Rn, okay, and you rotate it by an orthogonal matrix R, that doesn't change the length, right? That's one of the properties of orthogonal matrices. Okay, so the point is that we just can scratch the R. Okay, so this is 1/2 integral over the body. Okay, so now I'm going to, at the same time, do another expansion. And what I'm going to do is I'm going to do two things at once. The first thing I'm going to do is I'm going to expand the inner product, the norm, as an inner product. and then the second thing I'm going to do at the same time is I'm going to recall the definition of the hat map, or a property of the hat map, is that this is actually omega cross chi. Okay. And so you take the inner product of omega of t cross chi with omega of t cross chi mu of chi. All right. Okay, good. And now what I'm going to do is we're going to do an operation that's familiar to us from when we talked about the inertia tensor. And when we proved the definiteness of the inertia tensor, we actually saw exactly that expression show up. Okay. And the relationship of that expression with the inertia tensor is derived by a vector identity. And the vector identity is this one. Okay, and so we're going to apply this vector identity to the expression here, and you know, the effect of that is to move the cross product over there. Oops. Okay, so this is 1/2 integral over the body, inner product of omega of t with chi cross omega of t cross chi d mu chi. Okay, so now we can move the integral inside the inner product. Okay, and then in doing so, we see we're going to get the integral of that thing over the body, but with our assumptions, right, that is just the inertia tensor applied to the vector omega of t. Okay, and so the point is this is 1/2, and I'm going to write it in a different order. I'm going to write it like this. Inertia tensor with respect to the center of mass. That's a symmetric 3x3 matrix. Okay, it's symmetric positive semi-definite 3x3 matrix. Like that. Okay. All right, and so what we've shown is that the kinetic energy is equal to a nice sum, 1/2 m r dot of t squared plus 1/2 inner product I c omega with omega. Okay. Now, so something very convenient happens here, and that is that the kinetic energy breaks into a sum of two things, and each one seems to be quite identifiable. This is what you would want to call the translational kinetic energy, and this is what you'd like to call the rotational kinetic energy. Okay. All right. And so let's think for a minute about why we were able to come up with a decomposition and an additive decomposition of the kinetic energy into these two chunks of translational and rotational. So the key to that was were these assumptions, okay? Because these assumptions allowed us to show that in the expression for kinetic energy, this cross term, which we expanded out here, was equal to 0, all right? Now, the interesting thing, and this is going to show up in a couple of places, the interesting thing is that this is reflected in sort of a more elementary thinking about mechanics that you would have learned in a introductory physics course, where you found equations of motion for, you know, is what we're calling interconnected mechanical systems by summing forces and moments. Okay. And so, you took a body and you would, kind of isolate it and you write all the forces on it. And then you sum forces and sum moments. Forces are kind of unambiguous. You just sum them as vectors. When you sum moments, you have to sum moments about some point. Okay, and that point, it could be arbitrary, but in your mechanics course, you would have learned that there's two rules for how to choose the point about which you can sum moments. You can sum moments about two kinds of points. One is the center of mass. Okay, that's always good. The other kind of point about which you can sum moments is a stationary point, so a point that doesn't move in the spatial frame. Okay. So let's look at the effect of that. So if you sum moments about the center of mass, we see that that is reflected in our calculation here by our body frame having its center of mass at the origin, and we're going to use the inertia tensor about the center of mass. Okay, and the net effect of that was that this term was equal to 0. And really the crucial thing here was this part of that calculation, right? Which is that the center of mass is 0 in the body frame, and that's that assumption. Okay. And so we see the center of mass, the location of the center of mass is crucial here, in that if you place the body frame there, this cross term is equal to 0. Okay, and that's connected to the legitimacy or the validity of summing moments about centers of mass in your sort of free body diagrams and balancing forces and torques and stuff like that. Okay, now what about the other situation where you were permitted to sum moments about stationary points? Okay, well, what does a stationary point mean? Well, a stationary point is going to be one which doesn't move in the spatial frame. Okay, so if you were to place your body origin at a stationary point, okay, so let's assume that this was a stationary point, and it doesn't have to be the center of mass here. Okay, so let's suppose the center of mass may be over here somewhere for the purposes of what I'm saying now. Okay, so but I'm going to assume that this point in the body is stationary. Okay, so as the body moves, it just rotates about that point, and what that means is that r, okay, the vector r that you measure to that point, that's constant as a function of time. Okay, and so r dot therefore will be equal to 0, and again, the effect of that is that the cross term here in the calculation of the kinetic energy is equal to 0. And so the vanishing of this cross term, happens in two situations. One where the origin of the body frame is stationary, in which case little r dot is equal to 0, or if the origin of the body frame is at the center of mass, in which case we get that to be 0. Okay, so the decomposition of the kinetic energy into these two summands, and not having an ugly cross term in the middle is a result of is connected to something that you've seen in more elementary treatments of mechanics. Okay, and again, we're going to see that show up later on as well. Okay, good. Now what we want to do is we want to talk about not just kinetic energy of a single body, but kinetic energy of an interconnected mechanical system. So we have kinetic energy of an interconnected mechanical system. Okay, so we're going to consider an interconnected mechanical system with configuration, with m bodies, okay, and configuration manifold. Q in Q free, and Q free is always just some collection of products of SO3 cross R3. Okay. Now notice that we're going to always now be restricting to bodies. In the beginning, when we talked about Q free, we kind of allowed separately there to be particles, and so then we would have some collection of copies of R3 as well. We're not doing that anymore, and the reason is simply because what we've seen is that particles are just special cases of rigid bodies with a very specific inertia tensor, namely an inertia tensor, sorry, not inertia tensor, but mass distribution. And so for a particle, the mass distribution is just concentrated at a single point, okay? So we don't need separately to talk about particles. You can, but we don't have to. All right, so we have an interconnected mechanical system with some bodies and a configuration manifold. The system is in motion, just like when we talked about a single body. Okay, so this means I have a curve gamma in Q. Okay. All right. So if the system is in motion, and of course that just means that all of the bodies that comprise the system are also in motion, and they're in motion in such a way that they satisfy the constraints that are determined by Q. All right. Therefore, for each body, so for body A, we have the motion of the eighth body. Okay, and the motion of the eighth body, we had a way of determining that, and that was you determine the motion of the eighth body by taking the forward kinematic map, pi A, applying it to gamma. Okay, and so the forward kinematic map is a very simple thing. You take a point in Q, okay, which is also a point in Q free, and so it's a product of things like this, and you project it onto the eighth component of that product. Okay, and so this thing is going to look like, therefore, RA of T, little RA of T, and of course that's in SO3 cross R3. All right, and so the system being in motion like this puts each of the individual bodies in motion like this, and so for each body we're basically back in the situation that we talked about in the beginning. Okay, so you're undergoing some motion. Okay, and so you're just really the kinetic energy then is just m versions of the calculation that we just did. Okay, so the kinetic energy you obtain just by summing the kinetic energies for each of the bodies. Okay. Okay, so we have Ke of T, and so I'm going to now think of the kinetic energy as being a function of T, and it's just going to now, as I said, just be a sum. And so I'm going to take a sum of the terms just like I had here. Except I'm going to have the mass of body A, I'm going to have the kinetic energy of body A, I'm going to have little RA, and then omega A, right? But it's just a calculation that I did above. Like that, okay? So that's easy enough. The kinetic energy of the system is just the sum of the kinetic energy of each of the bodies that comprise the system. Okay. All right, so now what I want to do is I don't want to think of the kinetic energy as being a function of time. What I want to do is I want to think of it as being a function of position and velocity. Okay. And you can see that's indeed what it's going to be, velocity here, and in fact, omega also encodes, position as well. All right. And so this thing is, in fact, a function of position and velocity. Okay. But let's be a little bit sort of precise about that. Okay, so we now think of kinetic energy as a function. Okay, so it's going to be a function of position and velocity. And what does that mean? That means it's a function on TQ. Okay, that's what TQ does by the very construction of TQ is it gives us positions and velocities. Okay, all right, so it's easy to do that, but let's do it sort of in a systematic way, because it's a nice illustration of how all of our differential geometric tools can be used to make things clear. All right, so we're going to, so I'm going to define a function like so. So I need to take a point there. And so I'm going to choose a point v sub q. So v, the sub q means that I'm going to fix a configuration q, and I'm going to talk about a velocity vq at that configuration. Okay. So this one is going to be in the tangent space at q, and of course, this is just a point in TQ. All right, so every point in TQ has some point in Q that it sits at. Okay, and so I choose some velocity, and now I'm going to use the definition of what a velocity is, a tangent vector. I'm going to let gamma be a curve at Q. Okay, so that just means that gamma passes through Q at time 0, such that VQ is the equivalence class of gamma at Q. All right, and I know that I can do that because that's the definition of a tangent vector. It's an equivalence class of curves. Okay, so now given this connection of a tangent vector with an equivalence class of curves, okay, I've sort of put myself just exactly in this situation here, okay, of having the system in motion. And all I'm going to do now is, because gamma is a curve at Q, so that means that gamma passes through Q at time 0. Okay, so I'm basically just going to take all of this stuff and I'm going to evaluate it at t equals 0, and that's going to give me the kinetic energy at VQ. Okay, so K, so then kinetic energy at VQ is kinetic energy evaluated at t equals 0. So I'm making a convenient abuse of notation here, and I'm using the symbol KE for two different things. So this KE here is the thing I'm trying to define, okay, which is a function on TQ. This KE here is KE is a function of T that I've already talked about. Okay, so this is the same as that. Okay. Okay, so this is KE as a function of T, and this is KE as a function of VQ. All right, so again, an abuse of notation. All right. Okay, so that's how you define kinetic energy as a tangent vector using our expression for kinetic energy as a function of time along a motion. Right? You just take the kind of a derivative of the motion, and that gets you your at time 0. That gets you your tangent vector VQ, and then you just basically just substitute. Okay. So that gives you a computation that you can do. All right. What we're interested in, we'll look at how to do these computations, how to actually calculate the kinetic energy as a function on TQ in examples later. What I'm concerned with right now is what's the form of this function, or more particularly that function. Okay, so what are the properties of kinetic energy as a function on TQ? Okay, so it's not clear what that means right now, but we'll see what I'm getting at. Okay, in particular, what I'm really interested in most of all are the properties of kinetic energy as a function of velocity with Q fixed. In particular, if we fix Q, what are the properties of kinetic energy as just a function on the tangent space at this fixed Q? Okay, so freeze Q and consider this as a function just of velocity. What properties does that have? Okay, well, all right, there's our formula. Okay, and so I'm interested in how this varies with velocity. Okay, well, I see velocity kind of showing up here, you can imagine, in some way. This is the translational velocity, this is the angular velocity, and these velocities are related to this velocity. Okay, so let's try first to understand that. So first, we claim that RA dot of 0 and actually omega A at 0 are linear in VQ. Okay. Okay, so let's see, well, first what that means, and then why it's true. Okay, well, first of all, we have this. Okay, so we saw that already. Okay, so when we talked about how to break the motion of the body up into the motion of each of the system into the motion of each of the constituent bodies. Okay, all right, so we have this expression, which is really just the definition of these. All right, now, so I'm saying here something about the derivatives of little r, and this involves the derivative of capital R. Okay, and so let me just differentiate this relationship with respect to t. Okay, so on here I'm going to get RA dot t, and let me evaluate that at 0 because that's what I'm interested in. Okay, and I know that this is so omega is so this one is RA of 0 omega hat of 0. Okay, A. All right, and so the point is that this is a linear function of omega hat. Okay, so in other words, to establish my assertion here that these are linear functions of VQ, it's enough to establish that these are linear functions of VQ because this is a linear function of omega hat. Okay, all right, so now let's look at why these things depend linearly on VQ. And to do that, I'm going to differentiate this formula and I'm going to differentiate this composition using the chain rule. Okay, so I'm going to first differentiate this and then I'm going to compose it with the derivative of that. Okay, so the derivative of pi a, so pi a is a mapping between Q and SO3 cross R3, so that's a mapping between manifolds, and we differentiate those by T. Okay, so we're going to take the derivative of pi a, and we're going to differentiate that at the point gamma of T, where T is equal to 0. Okay, but this point is just Q. Gamma is a curve at Q. Okay, so this is, remember we wrote this down in coordinates, right? This is just the Jacobian in coordinates, right? So then we need to take the derivative with respect to T of gamma, and we did that, right? So we carefully, took a mapping from R into Q and looked at its derivative, and we introduced some notation for that, which was gamma prime, again, at 0. Okay, and of course, gamma prime at 0 is just VQ. That's my definition of the relationship here between VQ and gamma. Okay, and so you see, yes, that these things depend linearly on VQ because this thing is a linear map. Okay, again, in coordinates, it's just the Jacobian. All right, so that establishes this assertion that I made here, that these are linear functions of VQ. Okay, good. All right. And why did I do that? Why did I express these as functions of VQ? Because in the expression for kinetic energy here, we can understand very easily how the kinetic energy depends on little r(a) dot and omega. Okay, and it depends on these velocities. Okay, quadratically. Right, so this is the norm squared, right? So the norm squared, that's a quadratic function of velocity, right? And of course, this is 1/2 mv squared. And similarly here, the dependence on angular velocity is quadratic, right? So this is a symmetric 3×3 matrix times this thing. Okay. All right, so the point is this is a quadratic function of r(a) dot and omega a. Okay, so this thing is quadratic in r dot a of 0 and omega a at 0. Okay. All right, so this is a quadratic function of these. These are linear functions of that. And so therefore, this, which is, by our definition, Ke of VQ, is a quadratic function of V. Okay, so this function for fixed Q is a quadratic function. Okay. And the other observation that I can make here is not only is it a quadratic function, but it's also non-negative, right? So as a function of V, it's a non-negative function, and that's clear because that's non-negative. Okay, and I is a positive semi-definite symmetric matrix, so all of its eigenvalues are non-negative, right? Those are the principal inertias, and so when you calculate that expression, that's going to be non-negative. Okay, so KE at t equals 0 is, okay, and this is of course equal to KE of VQ is non-negative. Okay, all right, so we'll examine the repercussions of that next time.